Everybody, welcome to our presentation. I'm Celal Onur Gökçe from University, Turkey. So I would like to present our study about disturbance rejection performance comparison of particle swarm optimization and Ziegler-Nichols methods for various disturbance frequencies. So our presentation structure, in part 1 I will introduce the concepts, in part 2 I will talk about DC motor and control, in part 3 our materials and methods will be told, in part 4 I will talk about our results, and I will discuss some issues and conclude in part 5. So DC motor, direct current motor, is one of the most used electrical motors in the industry, and its speed control is very important for various applications. So it is a lot of advantages, and maybe only disadvantage is the brushes. The brush wear is a disadvantage, and constant maintenance is required. Disturbance for automatic control, one of the biggest problems is external disturbances. So here we are simulating sinusoidal disturbances, and we are using PID, proportional integral derivative control system, which is one of the most used controller in the industry. The structure of the controller is as follows. We have proportional component, integral component, and derivative component in parallel, which take error signal as input and produce control signal as output. I'm sorry. So, how will we measure the performance of our system? We are using three performance metrics. One of them is steady state error. The second one is maximum overshoot, and the third one is settling time. We are using these three performance parameters to measure the performance of our system. These are the definitions which can be found in any control book. We are using two methods. One of them is the Ziegler-Nichols method, which is the oldest and most classical one. It is taught in almost all automatic control books. We use it as a control method, as a parameter tuning method for PID control. And these are the parameters to be used for PID control. KP, KI, and KD we use. And the main controller, the newer optimization or tuning type is particle swarm optimization. It's an optimal control. The second method we used is particle swarm optimization method. Particle swarm optimization, we have used it in our other studies also, and we have shown that it's very efficient and effective method. So graphically, it's like we have several particles which are Kp, Ki, and Kd parameters of controller. So here we are using 2 dimensions, but actually it's 3-dimensional since we have 3 parameters. So we have how particle swarm optimization works. We have 3 main parameters. First is the speed of the particle. I'm sorry. Su alabilir miyim acaba? Su var mıdır? I'm sorry for the coughing. If I can take some water. Thank you very much.
I will for you.
So three components of the particle swarm optimization are first the speed of particle, previous speed of particle. Second is Pn-1, which is the particle's best known point. And the third is Gn-1, which is all swarms known best point. So we are using these three information to find the next optimal point of the particle. So it's an iterative method. So the position of each particle is computed iteratively for each iteration. Here is the flow chart of our algorithm for particle swarm optimization. So we are using realistic parameters for DC motor. We have used simulation. In our simulation, we have used the following: this motor, C22 L33 series DC motors. We used Python programming language and Spider IDE for simulation. We didn't use MATLAB. For Ziegler-Nicholas, we used classical Ziegler-Nicholas method. And for particle sum optimization, we have used this flow chart. And for simulation, we have used trapezoidal rule for differentiation and integral. So our results are the following. Red one, which is seen very briefly here, is the reference velocity. Blue one is Ziegler-Nicholas, and green one is particle sum optimization. So as you see, particle sum optimization tuned controller follows the trajectory almost perfectly, while Ziegler-Nicholas has some problem in following the trajectory. So for various frequencies, we have made simulations. This is for frequency of 75 Hz. This is for 100 Hz. So you can see for 100 Hz, there are seeable deviations even in particle sum optimization. This is for 150 Hz. This is 250 Hz. And this is 350 Hz of disturbance frequency. As the frequency of the disturbance increases, you can see that there are more deviations from the reference trajectory. So this is red one is reference trajectory, green one is particle swarm optimization tuned controller trajectory, blue one is Ziegler-Nicholas tuned controller trajectory. How about the disturbances? These are the disturbances we have used for various frequencies. As you see, as the frequency increases, the peaks become more close to each other as expected. So what we see, what's the result of the study? We see that for all disturbance frequencies, particle swarm optimization clearly beats the Ziegler-Nicholas method by far. This is the result of our study. Thank you for listening to me. If you have any questions, I am ready to try to answer.
Are there any questions?
Thank you very much.
Thank you.